elements help us in the tracking the carbonate diagenetic history. Okay? What we get that as you go to the more burial, there will be decrease in strontium, because strontium I expect to be more in case of aragonite, and if you go to burial, more aragonite will change to the calcite. So the strontium content in the carbonate that will decrease if you go to more burial, and your Fe and Mn, these two will be increased with more burial. Okay? To the anoxic stage. During the suboxic, the more manganese that will enter into the carbonate structure during the suboxic stage. Whereas in the anoxic, you get more of iron that will enter into the carbonate structure. Strontium decreases, manganese increases in the suboxic, iron increases. So I expect the more of manganese in the deep phreatic cement. And I expect more of iron in the deep burial cement. This basically helps that what is the relative percentage of the Fe, Mn, Sr. This actually helps in the identification of the burial history and the successive stages of the carbonate. So the trace element analysis involving these trace elements, that the increasing Mn content, increasing iron content, that talks about the more deeper burial diagenesis of the carbonate. This is also identified based on the cathode luminescence. Cl structure of the carbonate. The most Cl enhancement, that is the most the luminescence, more bright luminescence. When the carbonate will give the most bright luminescence? When the carbonate will have the highest Mn, manganese. With increasing iron entry, then the Cl image will be subdued. So I will get the maximum brightness of the Cl, maximum luminescence character of the carbonate when the carbonate will accommodate the maximum Mn. And that talks about the suboxic diagenesis condition commonly associated with the deep phreatic condition. And the high Mn with the subdued Cl, that will be talking about the deep burial cement. What about the stable isotope? Now, since carbonates heavily change by the diagenesis, and also carbonates often change by the dolomitization in the older carbonates, we will discuss dolomite in the next class. So in many cases, we think that the carbonate loses its original geochemical character, because diagenetically it is heavy altered, and dolomitization, if it happens to the carbonate, definitely the carbonate original geochemical character is lost. So it is a common practice that whenever we do any kind of carbon isotope analysis, the stable isotope analysis, that we try to see that how much the carbonate has been reset in terms of its character, geochemical character, or it is preserving its original geochemical character. How we do that? We basically make a cross plot of del 18O and del 13C. These two values, that we make a cross plot, bivariant plot. Once we identify these two values from the carbonate, through the IRMS, isotope ratio mass spectrometer. There are two types of mass spectrometer we use. What are the other type? What is the other type? ICP-MS, inductive coupled plasma mass spectrometer. It tackles the radiogenic isotope. It tackles the stable isotope. What is IRMS? Isotope ratio mass spectrometer. Now, in the IRMS, you identify the del 13C and del 18O, then you make a cross plot. If you see that it forms a linear trend, all the plots that is following, the correlation is very high. Correlation coefficient R square is very high, more than 0.5 to 6. If the correlation, that means both these isotopes, they are following one another, means the system is heavily reset. System is heavily reset because it has uniformly guided both the isotopic systematics. Though these two systematics, they are independent of one another. Oxygen isotope, it is a function of the temperature, seawater salinity and the seawater temperature, where the carbon isotope, it is a function of the biological productivity and basically the biological productivity. So carbon isotope is controlled by some other factor, oxygen isotope is guided by the other factor. They should not follow one another. If they follow one another, that means that there is some third factor which has guided both these factors, and that is a totally reset. But if they do not follow, that you have the so R square value that is less than 0.5, it is 0.3, 0.4. That means that the carbonate is still preserving its original character. Still preserving its original character. This is a very common diagram that people will always follow. And once that is followed, then you can use that carbon isotope data or oxygen isotope data for any kind of chemostratigraphic work. Commonly what happens, the more a carbonate goes into burial, the lighter isotope, the heavier isotope goes down and the lighter isotope is preferred. So what will happen that if a carbonate goes into burial is del 18O, that will be basically going lower and lower because of the higher temperature effect. So the lower del 18O value, of course, you see, if you have a high evaporation, then the whole thing changes. I am not going into that. General trend is that the del 18O value with the burial, it goes down, because del 16O become more prominent. Okay, and all these that basically help in the identity. So first of all, the petrography, the character, the texture of the different kind of cement, their mutual interrelationship. Then the different trace element, then the isotope, the cathode Cl character, all these together that help us in identifying the diagenetic character of a carbonate. Now what happens in a carbonate, you see, a carbonate, it forms in the ocean. It forms in the ocean. Then it may be uplifted because of any tectonic uplift or the closure of the ocean basin. As I discussed, even the top of Mount Everest, that is a carbonate, and that is the Tethyan carbonate. So the closure of ocean basin or this, that will expose this carbonate to the meteoric water. Then this carbonate can go into burial, and it can goes burial up to the deep burial stage. This carbonate can go up by another tectonic upheaval. So a carbonate starting from its deposition from the sea floor, it can go to the multiple history. It starts with the sea floor, then it goes to the meteoric, it goes to deep burial, it may go again up, that is the meteoric. And finally, in the process, what happens that all its original aragonite, high Mg calcite, all these now changes to the low Mg calcite. My work as a geologist is that what in between has happened. What has happened in the seafloor, in meteoric, in deep burial, and its uplift history, so that finally it has resulted this. All these that will be preserved, all the textures and the characters will be preserved in the final low Mg calcite. Your work is to find out all these histories that as the carbonate has gone through. Okay, so with this I am ending I am not further, because my next topic of carbonate will be carbonate platform geometry, carbonate platform. That I am not starting today. Carbonate platform I will be discussing in the next class. So this is, with this I end the diagenesis, carbonate diagenesis. I do not know that how far I am able to tell you the diagenesis, because diagenesis is a huge thing. Because it is this diagenesis that gives all the secondary porosity and permeability in the carbonate. It is this diagenesis that makes carbonate a beautiful reservoir of oil and gas. It is this diagenesis which makes the carbonate the beautiful reservoir of water. And this, all sorts of secondary porosity, in form of your bhags, in form of your karst, in form of your voids. So all these porosities, that basically is the storehouse of the different kind of fluids. And that's why the carbonate diagenesis is one of the most important thing for to understand before going for any kind of exploration program, any kind of venture, or any new area where you are thinking of a hydrocarbon reserve in a carbonate country. It is in the subsurface. And then unless you know the proper diagenetic history, then it is impossible for you to venture that where I should go for the hydrocarbon exploration, where I should not go for the hydrocarbon exploration. Now you see that in the carbonates, you are getting this carbonate cementation. Now if the cementation happens between the pore spaces, then all the pore spaces will be closed. So you will not get any hydrocarbon in the pore space, because pore spaces are filled by cement. So when the hydrocarbon has to be generated in the system, before the carbonates fill its full pore spaces by cement. So it is a very delicate thing that the organic matter that is maturing, and it has to release the hydrocarbon in that kind of condition when the carbonates have still has the porosity and not filled its porosity totally by the cementation. So before the cement, it is a contest. It is a contest where we get the hydrocarbon. It is a contest that when the hydrocarbon, the organic matter will be normally. What is the cooking temperature of organic matter? Cooking. You know what is the cooking temperature of organic matter? Have you already studied the petroleum geology? No. Hello?
No, sir.
Okay. So anyway, I am not going into that, but that is a fantastic story. That how really, but one thing you must understand, that if a carbonate reservoir, carbonate becomes a reservoir of oil and gas, then you have to put the oil and gas, because all oil and gas, they basically get accumulated in a reservoir by secondary migration. Where you get the oil and gas do not form there. Oil and gas form somewhere else, the source rock is somewhere, and it gets migrated and get accumulated in some other rock, which is a carbonate, because of its availability of the huge porosity and permeability. Now, if you already filled all the pore spaces by cement, then even if you have generated the oil, it cannot come and take its place. So you have to generate that hydrocarbon before you close the porosities by means of cementation. And that is a beautiful story on its own. But this itself requires another subject to discuss. Okay, so let us stop here. And in the next, I am really thankful to Aditi for yesterday and today. She has spared her laptop and so that I could take the class. And you all, if you people have learned something, you should be thankful to Aditi also. Not if at all, you people have learned something in my class. Hopefully by next week I will get my laptop and I will able to take class from my house. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, ma'am.
Thank you, ma'am.
Thank you, sir. Thank you, ma'am.